All right, thank you so much for joining us today. So, in the previous video, we talked about homogeneous differential equation and we were taking some example, which was fun, right? Now, we want to talk about what if the equation is not separable and at the same time not homogeneous. Then what can we do? Do we just leave the differential equation just like that, or we have a new way of doing it? Yes, we have a new way of doing it, and the new way is called exact differential equation. Now, if the differential equation is not separable and homogeneous, then the next thing that we need to think about is we need to think about exact differential equation. So we can see that this function here is not linear, this function here is not separable, and this differential equation here is not homogeneous. Can you see that? Because look at this. This is having a degree of 2, this is having a degree of 1. This is having a degree of 2, this is just a constant. So there is no way it's homogeneous. And it's not separable because we cannot separate the x from the y. So the only way to do this is to think about the exact differential equation. Let's talk about exact differential equation. So what is exact differential equation? So as we are learning, we see that every method that we talk about is having its special form. We talked about linear differential equation. We look at the form. Separable, you see how the form is. And then homogeneous too, we looked at how the function is supposed to be or the differential equation is supposed to be. Now, with the exact differential equation, we are saying that if we cannot do separable, if we cannot have it homogeneous, then we should have a function which is x and y such that I can multiply by the x, and then k in terms of x and y such that I can multiply by dy. What is this? Is this different from the homogeneous? Yes, this is different from homogeneous because homogeneous will be like p of x dx plus k of y dy. I said homogeneous, separable. So you see that this is separable because only x with the x, only y with the y. But this one is xy with the x, xy with the y. So that is the only difference here, right? So now what do we do? We are saying that this equation here is called the exact differential equation if when we differentiate the coefficient of the x with respect to y partially, it's the same as when we differentiate the coefficient of the y with respect to x partially. So when these two are the same, then we can say that this equation here is an exact differential equation. Let's take some example to understand exact differential equation before now we talk about how to use the method to solve. So what's the first thing that we need to do? Remember the standard form. This is the standard form. So we need to have something like this. So given 2xy plus 1 plus x squared plus 4y, y prime is the same as dy over the x. So what I need to do is I'll multiply through by the x. So I'm going to have 2xy plus 1 dx plus x squared plus 4y dy is equal to 0. So now this is the form, right? Because we need to write it in this form. P of xy dx plus k of xy dy is equal to 0. So we're able to write it in this form. So this will help us to find our p of x. So p of x is 2xy plus 1. So that's the coefficient of the x, which is here. And then also help us to find k of xy, what is the coefficient of dy, what is x squared plus 4y. So we said for this to be exact, then what do we need to do? When we differentiate p of xy with respect to y partially, should be the same as k with respect to x partially. So let's do that. Let's find the partial of p of x Now note that I can write this one as p of x. Just when you see something like this, mean as I'm taking partial with respect to x. So we are doing partial derivative. So what is this? What is this equal to? Let me just bring this guy here. What is this equal to? I need to differentiate this one partially. So I treat y as a constant and real values too as constant. So I'm differentiating x. This is going to give me 2y, because when I differentiate x, I get 1. When I differentiate 1, I get 0. Now let's work with this one too. Partial with respect to, oops, this one should go with y. So this is supposed to be y and this one should be x. So we said the p goes with y and then the q goes with x. Good. Then this one rather should go with x. It is q of x y, which is equal to q of y. Now let's differentiate this with respect to x. Let's differentiate this with respect to x. When I differentiate x squared, I'm going to have 2x. When I differentiate 4y, since there is no y, it's a constant. And when I differentiate it, it gets to what? 0. So what will be the conclusion here? We can conclude that since p of y is the same as k of x, the differential equation is exact. Very simple. So you see, any method or any other method that we are using have its own special way of solving it. So you need to master it by solving more examples, and then you'll be good at it. So basically that's how it is. And the more you solve example, the more you get used to the integrations and you become master of the integrations, because some of the integrations, it's so hard. Yeah. So what did I do? I write it in this standard form, which is this. I chose my p of x to be the coefficient of the x and my k of xy to be the coefficient of the y. Since this one is coming with dx, I need to differentiate this with respect to y and differentiate this with respect to x partially. So since this is 2x and this is 2x, this is the same as this, and we are saying that the differential equation is exact. Good. Now, since now we know how to talk about exactness, then the question is, now if the question is exact, then how can we solve it? So we are saying that if the equation this is the same as this holds, then there exists a function big F of xy such that my small p of x y is the same as the partial derivative of f, x and y, and my small q is big F of xy with respect to y. So this is what we are saying. So from here, if we want to solve, we are saying that since this holds and the function is differential equation, then we are saying that there exists a function, let's say f of xy, such that this my p of x here, right, is actually f of that, and f of y, this is q of xy. Now when you are doing ODE, you understand the standard form that we are writing here. This standard form here, this p of x here is just actually, if I'm using this one, this is basically f of x dx plus f of y dy. When you are doing advanced and those things, you understand total differentiation. So I differentiate the function with respect to x, then I multiply it by dx. I differentiate this one with respect to y, then I multiply it by dy. So now this f of x here is the same as the p of xy, and this is the same as the q of xy. So that's basically what we are trying to do here. Good. So that's what we are saying here. So if this one holds, then we have a function such that when I differentiate big F is the same as this, and when I differentiate big F with respect to y is also the same as this. Now when we are done with this, then we need have a process to go through. What's the process? we have two integrations, so we need to use them. The first one is integrate this with respect to x. So from equation 1, we want to integrate it with respect to x. So when you integrate this one with respect to x, we are going to have this, integrate this with respect to x. Now, we are come to add something. You see, anytime we integrate a function which is in terms of only one variable, we add a constant, let's say c. But this one is a function in terms of x and y. So we are going to add a function which is in terms of y, because we are integrating with respect to x. So we add a function in terms of what? Y. The question is, what if we are integrating with respect to y? Then we are going to add a function in terms of x. Good. Now, after we've gotten equation 3, what we need to do is we need to differentiate equation 3 with respect to y. The idea is that when we differentiate equation 3 with respect to y, we are going to get it to be the same as equation 2. So when you do that, then we equate the equation 3 to equation 2, then we find phi prime, we integrate, and then we find big F of xy, which is the same as a constant. So here, our big F of xy is the same as a constant. I know I'm talking plenty in your ears. I think example will do, right? Let's take an example. Always example always clears the doubt. So let's take an example and let's work through. So first, we need to check if it is what? Exact. So basically, that is what we just need to do. So with this one, always we need to check if it is exact before we can continue. So let's do that. First, the function is 2x plus 2y squared, or dx, plus 4xy plus 3y squared dy over dx is equal to 0. So we need the standard form. P of xy dx, k of xy dy is equal to 0, right? And then we need partial of y of p of xy should be the same as this guy x with the k of x. So this is two things that you need to know under exact differential equation when you start solving. So let's go through. I multiply through by the x, so I'm going to have 2x plus 2y squared dx, and then 4xy plus 3y squared dy, which is equal to 0. Now that I have this, now I need to pick my p of xy, k of xy. So what is p of xy? That's the coefficient of dx. So p of xy is equal to 2x plus 2y squared. And then k of, I can't even write it here. K of xy is equal to 4xy plus 3y squared. Now let's check if it is exact before we can use the exact differential equation. Now from here, let's find partial of p with respect to y. What are we going to get? Now we differentiate y. This has no y, so we go to 0. And when you differentiate y squared, what do you get? 2y multiplied by 2, and we get 4y. Now with this one, we take the partial of q with respect to x, and then this, there is x, differentiate the x, you get 1, so it is going to give us 4y. There is no x, so when I differentiate it becomes 0. So you see that this is the same as this. Good. So we conclude that since partial of p with respect to y is the same as partial of q with respect to x, then the differential equation is exact. So since this is exact, then one thing that we need to know here is there exists a function such that, you know, this is true, right? So let's say hence, or say it holds, since it holds, there exists a function, let me make it a big F of y, such that, so since this one holds, there exists this function such that when I differentiate this function here, with respect to x, I'm going to have p of xy, and p of xy was 2x plus 2y squared. Now, when I differentiate the same function with respect to y, I'm going to have k of xy, which was 4xy plus 3y squared. So basically, that's what we are doing here. So after you've gone through the process by checking it is exact, we are saying that there is a function. I mean, there was a function that we differentiated to have this. I mean, we are looking at the function that we differentiated and we had this function here. So there is this function such that when we differentiate the function with respect to x, we get the p of x, this. And then when we differentiate this with respect to y, we get q of x, which is this. So this is what we are having now, right? So I can call this guy equation 1 and call this guy equation 2. So now let's go through the process. It's very simple. It's very, very simple. Let's do that. You can start from equation 2 or equation 1, but you choose it based on how you can integrate fast. Good. So this one are all simple integration. So I'll start from equation 1. So from equation 1, we are going to integrate equation 1 with respect to x because this is x. So I integrate big F of x with respect to x, which is the same as integrating 2x plus 2y squared with respect to x. So that is what we are doing. So integrate this function and this function. Now, anytime we are dealing with this, since this function is differentiated, then when I integrate it, the differentiation will go. So this will just be big F of xy because it's differentiated and I'm integrating it. Now remember, we are integrating with respect to x. So when I integrate this, I'm going to have 2x squared divided by 2 plus, this is a constant without x. So when I integrate a constant, I just multiply it by x. So I'm going to have 2xy squared plus, now we know that when we do integration, we need to multiply the integration by, if the integration is indefinite, we need to add plus a constant. But you see that the integration that we are doing here is in terms of two variables, that is x and y here. So it means that we need to multiply, we need to add a constant, but the constant is not just a constant, but a function, which is in terms of y. We are picking y because now we are integrating the function with respect to what? X. The next question, I'll go first with equation 2 so that we can integrate with respect to y, and we see that this function here will be in terms of x. So don't forget, this is very important here. When you are done integrating this, we add a function which is in terms of y because we are integrating with respect to x. Let me call this guy equation star because this is like unique. Why am I saying that this is unique? This is unique because basically the function that we are looking for is this one. This is the function that we differentiated and we had this function here. So the only thing that we need to look for is we need to look for this function in terms of y and add it, and then we are done. So basically this is the general solution, but we need to find this guy. Now remember, we've made use of equation 1, so we need to make use of equation 2. How do we make use of equation 2? We can see that equation 2, big F of x, is partially differentiated with respect to y. So we need to differentiate our solution here with respect to y so that we can equate equation 2 and equation star, right? Let's move to the next page by writing that. So let me write my equation again there so that we can differentiate. So big F of x, y is equal to, what did we get? Okay, so let me simplify that. Let me simplify that in the other question so that I can now write it. So 2 cancel 2. So I'm going to have x squared plus 2xy squared plus 5 of y. So now this is my equation star. So I'm saying that we need to make use of equation 2. So we need to differentiate equation star with respect to y. So let's do that. When I differentiate this with respect to y partially, so xy, there is no y, so this will be 0. And when I differentiate this, I'm going to have 4xy. Because when I differentiate y squared, I'm going to have 2y. Multiply 2y to 2x, and I have that. Plus, now you see that this is a function in terms of y. So when we are differentiating it, we are not going to differentiate it partially. Because when you differentiate it partially, it's not going to work, because basically it's just in terms of only one function. So we are not going to do something like partial with respect to y this. No, we are going to differentiate it ordinary. So this is kind of dy, d over dy, that. This is what you are going to do. And this here, we can just basically write it as phi prime of y. Because remember, anytime we are using prime, it means that the function is in terms of only one variable. Good. So let me call this guy. So we know how to do this. So I'll just use phi prime of y. Let me call this guy equation 3. So now we see that we can equate equation 2 and equation 3. Why? Because this is big F of x with respect to y, right? And then this is also big F of x, y with respect to y. So it means that the right hand side here is the same as the right hand side here. So let's do that. The right hand side here was 4xy, 4xy plus 3y squared, 3y squared, which is the same as the right hand side of the equation 3. So 4xy plus y prime of that. So this is what you are going to get, but magic will happen. You know that phi prime of y is the same as 4xy minus 4xy plus y squared, 3y squared. So I move this guy to this side, become minus. So 4xy minus this plus that. So it means that we are going to have phi prime of y is equal to 3y squared. But the question is, look at equation star. We are looking for this, and this is just phi y, not phi prime y. So what we need to do is we need to get away with the what? The prime. So for us to get away with this one, we need to integrate. So we need to integrate. Now the function is in terms of y. So we are going to integrate this with respect to y, integrate this with respect to y. So when I integrate this, because this one is differentiated, this one will come with just the phi, and integrating this is going to give us 3y cubed divided by 3 plus, now you see that the function here is in terms of only one variable, which is y. So now we can add a constant. So you see the two difference here. Here we added a function of y because we are integrating two functions. One is x and one is y. So we need to add a constant y to it. So this is what you are getting. So now what can we do? We can just plug this one inside this. Inside this. So if I call this one, let's say equation 4, I will say put equation 4 into the special equation star. And we are going to have big F of xy to be equal to x squared plus 2x y squared plus phi of y, but phi of y is equal to this. Oh, I should have simplified this. I think I can do that. So this is going to be phi of y, which is equal to y cubed plus c. So let me now call this one equation 4. So this is y cubed plus c. Wow, wow. Now remember we made mention of something, that big F of x, y under exact differential equation is actually a constant, c. But see, we've made use of this c here, so we cannot use another c. So we can say that, or we can basically make this one, since we know that we can make this one c1 and make this one c1 so that we can maintain our c here. So what can we do here? Now we are going to have c is equal to x squared plus 2xy squared plus y cubed plus c1, and this is the same as x squared plus 2xy squared plus y cubed plus c1 minus c, which is equal to 0. And this is x squared plus 2xy squared plus y cubed plus k. A constant minus a constant is a constant. So I can even say c2. Or basically I can make this one c2, 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 so that I can make this one c. So this will be the general solution. This will be the general solution. So I hope you've understood the process. If not, you can rewatch the video again and then see the process. But I'll take another example that we are going to do it, and then it's going to help you to also go again with the process again, right? So now this question is, we've given this function here, a and b are constant. Find the values of constants a and b such that the equation is exact. So keywords, the equation is exact, meaning that the equation here is already exact. It means that when I differentiate p of x, y with respect to y, it's automatically the same as this because the function is exact. Remember, anytime the equation is exact, this is true. Is that right? So we can use this idea to find the constant a and b. So let's go through the process and then I'll show you. So let's talk about a. Now first we need to write this in the form pxy dx plus qxy dy, which is equal to 0. So let's do that. B ex cos y minus 3y plus minus ax plus e to the power x sine y dy over dx. So the first thing that we need to do is multiply through by the x, ex cos y minus 3y times dx plus minus x plus ex sine y dy is equal to 0. So let's pick p of x, that's the coefficient of this, q of xy, that's the coefficient of that. So p of xy will be equal to b is x cos of y minus 3y, right? And then q of xy will be equal to minus ax plus ex sine y. Now let's find for p of partial of this with respect to y. Good. So differentiate this with respect to y. What are we going to get? So we have y here. This is like constant multiplying this. So I just need to differentiate cos y. When I differentiate cos y, what am I going to get? Cos y is going to give us, I think, minus sine y. So this is going to give us minus bex sine y. Then when I differentiate this one too, I'm going to have negative 3. Then now I differentiate Q with respect to x. Differentiate this with respect to x, we are going to have minus a. And differentiate this with respect to x. This is constant because it's y. When I differentiate e to the power x, I get the same thing, plus e to the power x sine y. Now, the equation is saying that the question is saying that the equation is exact. So this is the conclusion that we are making. Since the equation is exact, then partial of p of y is the same as partial of q of x. Because the question is saying that it's exact, even though we don't know whether this and this are the same. But since the question is saying that it is exact, then it means that this is the same as that. So we need to equate this to this. So let's do that. With the p, we are going to have minus b e to the power x sine y minus 3 is the same as q is minus a plus ex sine y. So here we need to compare terms. So we can see that we have ex sine y here, and we have ex sine y here. So it means that these terms are the same, right? So the coefficient of this should be the same as the coefficient of that, because they are the same, right? So it means that minus b, which is the coefficient of ex sine y, is the same as the coefficient of this one here, but the coefficient of this one is 1. So minus b is equal to 1 and b is equal to minus 1. Now, this is a constant and I have another constant here, so these are the same. So this should be the same as that. So minus a is equal to minus 3 and a is equal to 3. Good. So it means that for this to be the same as this, and b should be minus 1 and a should be 3. Let's see. If b is minus 1, this becomes positive and is the same as this, right? And a is 3 and this one becomes 3 and also the same as that. So now we are done with a. We were able to find a and b, which is question A. Now question B is to find a particular solution of the differential equation. So as I said, since we want to find a particular solution, we need to find a general solution first. So now, since we know that the equation is exact, we can just go through the process and just check it out. So let's look at B. So B, we have B to be minus 1. So we just plug them in. So let me just pick this guy and go and paste it there. So B, now we want to solve this. But we know that B is minus 1 and A is 3, right? From this. Okay. So let's do substitution from this. This is going to give us minus ex cos, or even, okay, let me show you the shortcut. We've done everything, so we don't need to even go through the whole process. Since we want to solve for b, we can use this because we are just going to use this, so we can just use this, our p and q, because we don't need to go in and find all of them again. So let me paste it here. Good. Now we know that a is equal to minus 1 and b is equal to 3. So we are going to have the new p to be equal to 3. Is that what? No, I've changed it. So a is 3, b is minus 1. So I'm going to have minus e to the power x cos y minus 3y, right? And then my q of xy is equal to, I'm going to have, so here a is 3, so I'm going to have minus 3x plus ex sine y. So what are we getting here? Here basically what we are getting here is, now since this is exact, we've done the exactness already because the question told us that it's exact. So we need to just go ahead and say that there is a function such that blah blah blah, and then we just do that way. So we know that partial of p of x this is going to give us, when I differentiate this one with respect to y, we had this is going to be ex sine y minus 3, and then when I differentiate q with respect to x, I'm going to have minus 3 plus ex sine y. So we can see that this is the same as this when we put it inside. So we are saying that the differential equation, the differential equation is exact. It's exact, which the question even told us. So what we just need to do is, there is this, we start by saying that there is this a function, there is it a function, let's say small f of xy, such that such that such that when I differentiate small f of x with respect to x, I'm going to have p of x. Remember, we need to have p of x. So p of x is basically minus e x cos of y minus 3y. And then f of y of xy is equal to q of xy, which is equal to this. So that one is minus 3x plus ex sine y. So this is what we are going to get at the end of the day. So I call this one equation 1, I call this one equation 2. So that is the process that we need to just go through, and then we are done. So now let's do the integration. Here you pick the function that you can integrate the best. But the first one we pick equation 1. So this one I'll pick equation 2, so that we will know the other process too. But it's not because I pick equation 1, that's the reason I'm picking equation 2. But the idea is that I can also differentiate, I can also integrate equation 2 as well. So here you pick the one that you can integrate faster. So from equation 2, we are going to integrate with respect to y, because this is differentiated with respect to y. So let's integrate with respect to y, and then minus 3x plus e to the power x sine y, integrate with respect to y. So when I do the integration here, we'll be left with f of xy, which is equal to, so what are we going to get? Integrate this with respect to y. This is a constant. So I'm going to have minus 3xy plus, now I want to integrate sine y because this is constant. When I integrate sine, what am I going to get? I'm going to get minus cos. So this is going to give us minus es cos y plus, good. Now we are integrating with respect to y. So our constant function here, or our function here, should be in terms of x. So that's the reason why I chose the equation 2, so that we will know that, okay, now that we are integrating with respect to y, the function should be in terms of x. And we know that this should be the equation star, right? So now we've used equation 2. So we need to use equation 1. So you saw that the first one we used equation 1, and then we needed to use equation 2. So we differentiated the equation star with respect to y, because we needed to use equation 2. Now that we need to use equation 1, this is differentiated with respect to x. So we need to differentiate equation star with respect to x. So this is going to give us fx xy to be equal to, now we are differentiating with respect to x. So this is going to give us minus 3y minus es cos y plus 5 prime of x. So what did I do? Differentiate this with respect to x, it will be this. When I differentiate this, I get the same thing. So I get the same thing here, plus this. And don't forget, we are doing partial derivatives. So that's the reason why we are not using the idea. So this one is like a constant. So when I differentiate this, I multiply by the constant. Let me call this guy equation 3. So now we can see that equation 3 and equation 1 are the same. F of x, f of x. Right. So I'm going to equate equation 3 and equation 1. So what am I going to get? I'm going to have minus 3y minus ex cos y plus phi of x, which is the same as equation 1. Equation 1 is minus ex cos y minus 3y. So I equated this to that, right? So what do I need to do? Now we can see that this will cancel this and this will cancel that, right? Because when I move this one to here, it becomes positive. So negative positive becomes 0. When I move this one here, it becomes positive. Positive negative will be 0. So it means that we are going to have phi prime of x to be equal to 0 from here, right? So when I simplify this, this will cancel this, this will cancel this. So phi prime of x is equal to 0. So now since from equation start we need phi of x, then we need to integrate this. So integrating phi prime of x dx is equal to integrating 0 dx. This is going to give us phi of x, and when I integrate 0, I get 0, but I need to add constant because we know that when we differentiate a constant, we get 0. Good. So now that I know phi of x, let me call it equation 4. I'll put equation 4 into my special equation, equation star. So let's go for equation star. Equation star is here. So let me just copy that. Good. So now this is equation star. So we want to put this into equation star. So we are going to have f of, oops, this is not equation star. Wrong choice. Equation star is here. This is equation star rather. Good. So we have equation star. So when I put, I'm going to have f of xy, which is equal to minus 3y minus ex cos y plus, let me make this one c1, so plus c1. Then we know that always this f of xy is a constant, so let me name it, let's say c2 minus 3xy minus ex cos y plus c1 minus 3xy minus ex cos y plus c1 minus c2 is equal to 0. And I'm going to have minus 3xy minus ex cos y plus c is equal to 0. So this is my general solution. This is my general solution. But we know that I think they gave us initial condition here. So we need to use the initial condition on the general solution to find the constant. Now we know that y of 0 is equal to 0. This implies that y is 0 and x is 0. So now let's go from this one. We are going to have minus 3 times 0 times 0 minus e to the power 0 cos of 0 plus c is equal to 0. So this will be 0 minus, this will be 1 times 1 plus c is equal to 0, and c will be equal to 1. So it means that we are now going to have a big minus 3xy minus a big ex cos y plus a big 1 is equal to 0. And this is the particular solution. Good. This is the particular solution. So this is how exact differential equation works. Check if the function is exact, and then we go through the process by doing the whole of this. Now I'll give you a trial question to do. Yes, I have a trial question here. First, check if this is exact. When you are done, solve this equation by finding the general solution and using the initial condition to find the particular solution. Yes. Now, in the next video, we are going to talk about, let's assume that the function is not separable, it's not homogeneous, and we're thinking about exact too, and it is not exact. Example, we are going to assume that partial of P with respect to Y is not the same as partial of Q with respect to X. Then what next? What do we need to do? So that's what we are going to look to in the next video. So see you in the next video, and don't forget to drop your final results in the comment section. See you in the next video.